Hello. Good morning, friends. My name is Dr. Sanjay Pargania, guest lecturer from Government Digvijay PG College, Rajnandgaon. And this video lecture is regarding the quantum mechanics second semester paper 1, and the today's topic is the angular momentum operators and their representation in spherical polar coordinates. So we come to the lecture, and as we know that in classical mechanics, the angular momentum of a particle is defined through the relation L is equal to R cross P. This is equation number 1. Here R is the position coordinate, that is R is equal to xi plus yj plus zk, and the P is the momentum. In vector form it is written pxi plus pyj plus pzk. Now from the definition of R cross P, this can be solved by the determinant method, and from this we can obtain the three components of L as Lx is equal to ypz minus zpy, Ly is equal to zpx minus xpz, and Ly is equal to xpy minus ypx. And in vector form, L can be written as Lxi plus Lyj plus Lzk. Now, in quantum mechanics, we replace these quantities by the operators. As we know that the position operators are x, y, z simply, and the momentum operators are written as px. This can be represented by minus ih cross del upon del x. Py can be represented by minus ih cross del upon del y, and pz is represented by minus ih cross del upon del z. Then Lx is equal to, we can write minus ih cross inside the bracket y del upon del z minus z del upon del y. Ly is equal to minus ih cross inside the bracket z del upon del x minus x del upon del z, and Lz is equal to minus ih cross inside the bracket x del y minus y del x. Now, to transform this momentum or the angular momentum operators in spherical polar coordinates, we use the transformation equations x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. And the inverse transformation equations are r square is equal to x square plus y square plus z square, and tan square theta is equal to x square plus y square divided by z square, and tan phi is equal to y upon x. Now we need to find the various partial differentials. First we find del x upon del r, and this is equal to this can be obtained by differentiating the equation x is equal to r sin theta cos phi with respect to x partially, and this is equal to sin theta cos phi. Similarly, we can obtain del y upon del r is equal to sin theta sin phi, and del z is equal to r del z upon del r is equal to cos theta. And the partial differentials of r with respect to x, y, z, this can be obtained by differentiating equation r square is equal to x square plus y square plus z square partially with respect to x, y and z respectively. So that del r upon del x is equal to x upon r, del r upon del y is equal to y upon r, and del r upon del z is equal to z upon r. And similarly we can obtain the partial differential of theta with respect to x, y, z, that is del theta upon del x, differentiating the equation tan square theta is equal to x square plus y square upon z square, we come to the result directly, and this is equal to cos theta cos phi upon r. Similarly, del theta upon del y is equal to cos theta sin phi upon r, and del theta upon del z is equal to minus sin theta upon r. And in similar manner, del phi upon del x, and this is equal to minus sin phi upon r sin theta. Del phi upon del y is equal to cos phi upon r sin theta, and del phi upon del z, this becomes equal to 0 because phi is independent of z. Now we know that del psi upon del x, this is equal to del psi upon del r into del r upon del x plus del psi upon del theta dot del theta upon del x plus del psi upon del phi dot del phi upon del x from the definition. Now putting the values of del r upon del x, del theta upon del x and del phi upon del x in this equation, finally we obtain the operator del upon del x. This is equal to sin theta cos phi del upon del r plus cos theta sin phi upon r del upon del theta minus sin phi upon r sin theta del into del phi in spherical polar coordinates. In similar manner, we can obtain the operators del upon del y. This is equal to sin theta sin phi del upon del r plus cos theta sin phi upon r del upon del theta plus cos phi upon r sin theta del upon del phi. And finally del upon del z is equal to cos theta del upon del r minus sin theta upon r del upon del theta. Now using these values of del x, del upon del x, del upon del y and del upon del z from this equation 6, 7, 8, putting it in equation 3, we get the momentum operator, the angular momentum operator Lx is equal to IH cross inside the bracket sin phi del upon del theta minus cot theta cos phi del upon del phi. Similarly, the momentum operator, the angular momentum operator Ly is equal to IH cross inside the bracket minus cos phi del upon del theta plus cot theta sin phi del upon del phi, and Lz is equal to minus IH cross del upon del phi. And the operator L square is defined as L square is equal to Lx square plus Ly square plus Lz square, where Lx square is equal to Lx dot Lx, and by putting the different values, L square is equal to minus H cross square inside the bracket 1 upon sin theta del upon del theta inside the bracket sin theta del upon del theta plus 1 upon sin square theta del square upon del phi square. So these are the operators Lx, Ly, Lz and L square in spherical polar coordinates. We will continue this topic and wait for the next video lecture. Thank you.